Hello everyone. So in today's video, we are going to go over this paper, Semi-supervised text style transfer, cross projection in latent space by Mingwei Zhang, Pizhi Li, Zhenzing Fu, Li Dongbing, Dongyan Zhao, Zuming Shi, and Ruyan. I'm really sorry if I mispronounce any of those names. So they are from Guangzhou Institute of Computer Technology, Peking University, China, Tencent AI Lab, Shenzhen, China, Center for Data Science, China, R&D Center, Singapore, Machine Intelligence Technology, Alibaba Damo Academy. So they have one or more affiliations. So they've been listed here. So the abstract textile transfer task requires the model to transfer a sentence of one style to another style while retaining its original content meaning, which is a challenging problem that has long suffered from the shortage of parallel data. In this paper, we introduce a semi-supervised textile transfer model that combines the small-scale parallel data with the large-scale non-parallel data. So this is why it's semi-supervised. With these two types of training data, we introduce a projection function between the latent space of different styles and design two constraints to train them. We also introduce two other simple but effective semi-supervised methods to compare with. To evaluate the performance of the proposed methods, we build and release a novel style transfer dataset that alters sentences between the style of ancient Chinese poems and the modern Chinese. All right. So the primary reason why I was interested in this paper was because I was looking for works which were in the domain of semi-supervised textile transfer, and to my surprise, there are very few works in this domain. In fact, they on one other I could only find two papers, and I've already made a video on another one which was on politeness transfer. So it was also semi-supervised task. So let's have a look at this paper now. So introduction. Recently, the natural language generation tasks have been attracting the growing alien attention of researchers, including response generation, machine translation, automatic summarization, question generation, etc. Among these generation tasks, only one interesting but challenging problem is textile transfer. Given a sentence from one style domain, a style transfer system is required to convert it to another style domain as well as keep its content meaning same. As a fundamental attribute of text, style can have a broader and ambiguous scope, such as ancient poetry style versus modern language style, and positive sentiment versus negative sentiment. Alright, so there's a corresponding author and their email, and this work was done when Mingwei Zhang was an intern at the Tencent AI Lab. Alright, so this is just basically summarizing what is a textile transfer problem. I'll just show use a whiteboard to explain. So I've already explained it countless times in other videos since I've been making a lot of textile transfer videos. So if you have a sentence 1 to a sentence 2, this is a textile problem. If you have these constraints, so each sentence has a content and a style, right? So let's say this is style 1. Suppose you enforce the style to be the same, but you manipulate the style to become style 2. So you tell it, okay, become a sentence of style 2. So this problem is a style transfer problem because you are retaining the content. So the content is same, only the style is being transferred. So here is a transfer, right? So building such a style transfer model has long suffered from shortage of parallel training data, since constructing the parallel corpus that will align the content meaning of different styles is costly and laborious, which makes it difficult to train in a supervised way. So basically what they're saying is, suppose you want to do this. So if you are using totally labeled data, or say a supervised method essentially, then you'll need the same sentence in both styles with the same content. And you might assume why it is so difficult to get such data, because such data is not there in the wild. You don't really find people producing the same content in different styles again and again. So you'll need to like manually get this data, and then that would be a very expensive and time taking process to do because you need a huge amount of data. So when you go unsupervised, you use all these huge corpuses. So to compete with them, you need like some reasonable amount of label data as well. Uh, right. Even some parallel corpora are built, they are still in a deficient scale for neural network based models. To tackle this issue, previous works utilize non parallel data to train the model in an unsupervised way. One commonly used method is disentangling the style and content from the source sentence. So, this was there in a lot of works. For the input, they learn the representations of styles and style independent content, expecting the latter only keeps the content information. Then the content only representation is coupled with the representation for style that differs from the input to produce a style transferred sentence. The crucial part of such methods is that the encoder should accurately disentangle the style and content information. However, Lampel et al. Illustrated that disentanglement is not a facile thing, and the existing methods are not adequate to learn the style independent representations. So, what these works used to do was they used to take a sentence and create its representation. So two representations, one with style, which was this. So essentially, they learn the representation of style and the style independent content. So they learn, okay, what is this st1 and what is this c. So this, but you might now wonder how do you exactly distinguish between these two, right? Because some words bring style, some say archaic word might bring an old English style and also bring content. So this is why other works showed that this was not like a very good way to go ahead with, but it also gave reasonable results. Considering the above discussed issues, in this paper, instead of disentangling the input, we propose a differentiable encoder-decoder based model that contains a projection layer to build a bridge between the latent spaces of different styles. Concretely, for text in different styles, the encoder converts them into latent representations in different latent spaces. Right? We introduce a projection function between two latent spaces that projects the representation in the latent space of another of one style to another style. Then the decoder generates an output using the projected representation. So, like, I guess we should just wait a bit until they explain this paragraph more because this is the first time I'm reading this paper as well. So I think since this is the main idea, they'll explain it maybe a bit more in depth later. In the majority of cases, non-parallel corpora of different styles are accessible. Based on these datasets, it is feasible to build small-scale parallel datasets. Therefore, we designed two kinds of objective functions for a model so that it could be trained under both supervised and unsupervised settings. With the parallel data, the model learns the projection relationship and the standard relationship representation of the target latent space from ground truth. Without the parallel data, we trained the model by back projection between the source and target latent space so that it could learn from itself. During training, we incorporate these two kinds of signals to train the model in a semi-supervised way. So basically, they're using these two signals, one for the parallel and one for the non-parallel case, to generate to sort of train the model. So we conduct experiments on English formality transfer task that alters the speech between formal and informal styles, and a Chinese literal style transfer task that alters between ancient Chinese poem sentences and modern Chinese sentences. We evaluate the performance of models from the degree of content preservation, the accuracy of the transferred styles, and the fluency of sentences using both automatic metrics and human annotations. Experimental results show that our proposed semi-supervised method can generate more preferred output. Alright. So in summary, we designed a semi-supervised model that crossly projects the latent spaces of two styles to each other. In addition, the model is flexible in alternating the training mode between supervised and semi-supervised. So they got this point across well. We introduce another Another two semi-supervised methods that are simple but effective to leverage both the non-parallel and parallel data. We build a small-scale data set, right? Uh, so, so now, so now some related works. Recently, textile transfer has stimulated great interest of researchers from the area of neural language processing, and some encouraging results are obtained. In the primary stage, due to lacking of parallel corpus, most of the methods employ unsupervised learning paradigm to conduct the semantic modeling and transfer. So unsupervised learning methods like Muller et al. Modify the latent variable of sentences in a certain direction, guided by a classifier to generate the sentence with classifier favored style. Who et al. Employ variational autoencoders, Kingma and Welling 2013 to conduct the style latent variable learning and design a strategy to disentangle the variables for content and style. Shen et al. First mapped the text corpora belonging to different styles to their own space respectively and leveraged the alignment of latent representations from different styles to perform style transfer. Shen et al. Proposed to extract and control the style of the image caption through domain layer normalization. Prabhumoy et al. 2018 and Zhang et al. 2018b employed a back translation mechanism to ensure that the input from the source style can be reconstructed from the transferred result in the target style. Liao et al. 2018 associate the style latent variable with a numeric, discrete, or continuous numeric value and can generate sentences controlled by this value. Among them, many use the adversarial training mechanism, Goodfellow et al., so basically GANs, to improve the performance of the basic model. So we've had a look at some of these strategies in other videos. So this was like a good overview of the different techniques which have been used. To sum up, most of the existing unsupervised frameworks on the textile transfer focus on getting the disentangled representation of style and content. However, Lampel et al. 2019 illustrated that disentanglement not adequate to learn the style independent representations. Thus, the quality of transfer text is not guaranteed. Right. So we now have a look at the supervised, sorry, the supervised learning methods. So fortunately, Rao and Tetrol 2018 released a high-quality parallel dataset GYAFC, which consists of two domains for formality style transfer, entertainment and music, and family and relationship. The quantity of the dataset is sufficient to train an attention-based sequence-to-sequence framework. Nevertheless, building parallel corpus that could align the content meaning of different styles is costly and laborious, and it is impossible to build a parallel corpus for all the domains. So this is like one work, but for every work having parallel corpora is between two pairs is not like possible. So now the formulated task. So we assume two non-parallel datasets A and B that are sentences in two different styles, denoted as SA and SP, and a parallel dataset P that contains pairs of sentences with two styles. The size of the three datasets are mod A, mod B, and mod P respectively. As the non-parallel data is abundant but the parallel data is limited, size of A comma B is like very large compared to P. So basically what they're saying is that your parallel dataset is much smaller. Formally, two non-parallel datasets are denoted as A this and B this, right? So each sentence, and you have up to mod A and B1, B2 up to mod B, where AI and BI refer to ith sentence of style SA and style SB respectively. It should be clear that SA and SB are non-parallel. The sentences in the two datasets are not aligned, so AI and BI are not required to have the same meaning. So that even though they have the same subscript, so they just mention so that we do not get confused. So the parallel data set is denoted by A1 and a subscript P in these tuples sort of, where AIP, BIP is the ith pair of sentences that have the same content meaning but expressed in style SA and SB respectively. Due to the situation that the limited parallel data is deficient for neural network based model to train, our goal is to train a model in a semi-supervised way that could leverage the large volumes of non-parallel data to improve the performance. So they are also, it's not like they're only focused on the parallel data because they know they are limited by volume. So they are now they also want to incorporate a non-parallel data, so hence this is semi-supervised work. So given a sentence of the source style as input, the model learns to generate a target style output, which preserves the meaning of input to the greatest extent. In this paper, the style transfer process could be exerted in two directions, SA to SB as well as SB to SA. So now let's have a look at the model architecture. The textile transfer task could be interpreted as transforming a sequence of source style words to a sequence of target style words, which makes the sequence to sequence framework a suitable architecture. Since sequence to sequence is basically you input a sequence, you get out, you take output, you take a sequence as output. So an S2S model, which contains an encoder, a decoder, and our proposed models are built on such an architecture. So given an input, the encoder first converts it into an intermediate vector, and the decoder takes the intermediate representation as input to generate a target output. So in this paper, we implement the encoder by bi-LSTMs, so bidirectional long short-term memory, and the decoder by a one-layer LSTM, formally with an input sentence X. So you have all these uh, words in X, so W1X all the way up to WTX because the sentence is length T, and the target sentence Y of length T dash, where WI is embedding of ith word. The probability of generating the target sentence Y given X is defined as, okay, so this is basically you are iterating over all the sentences. So using a you are generating a target sentence using a source sentence. So when I is 1, you will be generating the first sentence using only X, the first word. Then you will for the second word you will use uh, sorry, for the second word when I is 2, you will use X as well as the first word which you generated and so on. So in the training process, the encoder first encodes X into an intermediate representation CX. More specifically, at each time step t, the encoder produces a hidden state vector HT. So one is the forward and one is the backward hidden state because this is a bidirectional LSTM, and this means concatenation. So both of them are concatenated to give one hidden state vector. The intermediate vector is formed by the concatenation of the forward and backward last hidden states denoted as Cx is equal encoder X, right? So then the vector is fed to the decoder to generate a target sentence step by step as formulated in equation 1. So you'll first I is 1, you'll get a probability and then so on. Such neural network based models always have a large amount of parameters which empower the model with the ability to fit complex datasets. However, when trained with limited data, the model may get so closely fitted to the training data that it loses the power to generalize. So basically, it overfits. So it performs poorly on new data. So now let's have a look at their method, uh, the novelty base, so to say, the cross projection in latent space. In this paper, we propose a semi-supervised style transfer method named cross projection in latent space (CPLS) to leverage the large volumes of non-parallel data as well as the limited parallel data. Based on the S2S architecture, we considered a representation in the latent space and proposed to establish projection relationships between different latent spaces. So, I guess this part was a bit self-explanatory. So, based on the sequence-to-sequence architecture, they since the sequence-to-sequence also has this encoder-decoder framework, so here also they are sort of taking a look at the latent space, and they want to have a look at the relationships and project stuff between different sorry, between different latent spaces. So to be specific, in the S2S architecture, the encoder converting the input into an intermediate vector is a process of extracting the semantic information of the input, including the style and the content information, right? So thus the intermediate vectors could be seen as the compressed representations in the latent space of the inputs. Since text in different styles are in different latent spaces, we introduce a projection function to project the intermediate vector from one latent space to another. So basically what they're saying is, suppose you have a polite sentence, you have a latent space representation for it, and then you have an impolite sentence, you have a latent space representation for it. So then they pick up things from that polite representation and project it onto the non-polite one. To combine the non-parallel data and parallel data in training, we design two kinds of constraint for the projection functions. Concretely, we first train an autoencoder for each style to learn the standard latent spaces of the style. After that, we train the projection function, which are exerted on latent vectors to establish projection relation between different latent spaces. Alright, so let's break this down. We first train an autoencoder for each style to learn the standard latent space representation of each style. So I guess this is pretty self-explanatory. They'll put in sentences and it will generate latent space representations, but you need good latent space representations, so you will train the model. So, and after that, we train the projection functions, which are exerted on latent vectors to establish projection relation between different latent spaces. So these sort of relationships between different latent spaces. So you need to train some sort of functions to do that. So these are what they call projection functions. So let me just mark this stuff. Right. So we design a cross projection strategy and a cycle projection strategy to utilize the parallel and non-parallel data. These two strategies are exerted iteratively in the training process. Thus, our data is compatible with the two types of training data. The model is compatible. So for the sorry for the non-parallel one, you will probably be using the cycle one. And for the other one, you can use the direct cross projection strategy. The following subsections give the details of the modules and the strategies of model training. Well, let's have a look at. Okay, let's just read, and when figure 1 pops up in the text, then we'll have a look at it. Because don't think it has so far. Right. Denoising autoencoder. To learn the latent space representation of style, we train an autoencoder for each style of text through reconstructing the input, which is composed of an encoder and decoder. So this is like your classic encoder decoder framework. The encoder takes input sentence and maps the sentence to a latent vector representation, and the decoder reconstructs the sentence based on the vector. But a common pitfall is that the decoder may simply copy every token from the input, making the encoder lose the ability to extract the features. To alleviate the issue, we adopt a denoising autoencoder following previous work that tries to reconstruct a corrupted input. So you forcefully corrupt the input earlier by adding some sort of noise. Specifically, we randomly shuffle a small portion of words in the original sentence to the corrected input, which are then fed to the denoising autoencoder. For example, if the sentence is listen to your heart in the mind, corrupted version could be listen your to and heart to your mind. The decoder is required to reconstruct the original sentence. All right. So the training of the DAE model relies on the corpus of one style only. Thus, we train each DAE model using the non-parallel corpus of each style. So you only pick up sentences from one particular style and you feed it to an encoder. You add noise, you feed it to an encoder, you get a bot latent space representation, then you send it to a decoder, you try to get back the original sentence, and you train the model on this process only. So the training of a DAE model relies on corpus of one style only. Thus we train each DAE model using the non-parallel corpus of each style. Formally, the encoder and decoder style SA and SB are referred as encoder A and encoder B, decoder B. So given sentences A and B from two styles, the corresponding encoder takes the sentences as input and converts it to the latent vector CA and CB respectively, by which each encoder therefore constructs the latent space for the corresponding style. So I guess this is pretty self-explanatory now. You have an encoder block and a decoder block, and you have a dataset. Let's say dataset K. Then you have encoder EK, decoder DK. You add noise and send it. So you add some noise. Sorry for that handwriting. You get a hidden space representation, latent space. Then you send it through the decoder and you get back the sentence. So you now want to get back K, and then you try to minimize the uh, difference between these two. So if the closer they are, the more accurately your encoder and decoder are working. All right. So I guess this part is now clear, denoising autoencoder. Now let's have a look at cross projection. So to perform the style transfer task, we establish a projection relationship between the latent spaces and cross-link the encoder and decoder from different styles. All right. So take this transfer from style SA to SB for example. So given a sentence A that is required to be transferred to B, we cross-link the encoder A as the encoder and decoder B as the decoder to perform style transfer modeling. Okay, all right. So basically, they'll pick up this section and then they'll pick up this section. So input A will go to the encoder of A to get the latent space representation, but it would not be decoded by the decoder of A, it would be decoded by the decoder of B, which generates sentences in style B. So, however, considering the DAE models for different styles are tra- uh, trained, therefore the latent space vectors are usually different. So, of course, since you've trained on dataset for B, then you don't expect it to perform well when you give it the latent space of dataset A, right? So the latent vector produced by encoding A is the representation on the latent space of style A, while this is relies on information features from the latent space of style B. Therefore, we introduce a projection function to project the latent vector from the latent space of SA to SB. Concretely, after we get the CA from encoder A, CA is basically latent space representation. Uh, a projection function is employed to project CA from the latent space of SA to the latent space of SB. So basically, you just apply this function of the latent space vector of A and then you get 1 for B. Then the decoder B takes the projected vector as input and generates a sentence B of style SB based on the prediction probability denoted by this. So you predict uh, B based on this vector, this projected vector CV. So basically what they're saying is, uh, I'll just use this photo if possible. Right. Uh, they'll send a sentence through here, it will go here, but their ultimate plan was to use the encoder of A and the decoder of B. But directly doing this naively is like stupid, right? Why would this even work? So they'll take the latent space of a sentence in the latent space of A, and then learn a projection to the latent space of B and then convert it like this. So this is much better because then you are leveraging your training as well, because then your training might generate different sort of uh, structures itself for how the latent space of A and B look like. So basically these mapping functions are then used. So FA is a mapping from A to B, and this is, so CB used to be your vector, latent space vector. C tilde B is like the converted one, and G is from B to A. All right. So this, I guess this makes sense now. And then basically you are going to predict B tilde, which is basically this, using this C tilde B. So now this is modeled as the probability of getting B tilde from C tilde B, which is basically this. So it is worth noting that we have only exploited a non-parallel corpus for style transfer up to now. Recall that a framework can employ both parallel and non-parallel. So with the parallel corpus, we designed a cross projection strategy. When the input A is accompanied with the ground truth table B, we can get the standard latent space representation of B by the encoder B denoted by CV. In order to align the latent vectors from different spaces, we designed the constraints to train F from two aspects. The distance between C tilde B and CB in the latent space should be close. The generated sentence B tilde should be similar with B. And then we define two losses. So up to now, we only discussed for non-parallel ones, but since they also have the parallel ones, so they're explaining the strategy for that. So for that one, that for the parallel one, they take the input, encode it, get the latent space representation, transfer it, and get this C tilde B. But since they also have B itself, which is the expected output, so they can also get the latent space representation of B directly. And they do that by uh, just passing it through the decoder of B. And since they want to minimize this distance, they between the projected one and the actual one, so they just use the difference, so the norm of the difference. And for the second loss, they have the loss of predicting the original sentence B, since they have the ground truth label, using the projected latent space vector. And then net loss, so this is a minus log likelihood, negative log likelihood as mentioned. And the net loss is just an alpha, so a weight given to the difference between the latent space representations and the weight given to the different the token generation. So this token generation based on CB tilde. So predicting B based on the transferred latent space representation. So this also shows that effectively, I guess. So figure 1 shows the training process of cross projection similar to transfer and style of text transfer. From SB to SA, we cross-link encoder B and decoder A, and the projection function to project CB to a latent space of SA is denoted by G dot. Alright, so we now have the cycle projection enhancement. Inspired by the concept of back translation in machine translation, we designed a cycle projection strategy to train the model on the non-parallel data. So given the input without the ground truth, we train the projection function f and g by projecting back and forth to reconstruct the input. The cycle projection loss is given in so this one. So you first get this CB tilde, then you use that to get CA tilde and so on. So you can then use that to again get CAB tilde 2, and then you see the difference, like the how far apart are they in the latent space and so on. So formally for a sentence A in style A, after getting its latent representation C in its own latent space, you project it to a latent space SB and you get this. Then we exert G to project it back to A, and A is again given to the decoder of A to produce an output A tilde. So though the latent vector CB dash has no reference to train, the latent vector CA dash and output A dash could be trained by treating CA and A as the references. So the loss functions are like this. So uh, when you are getting the CA tilde from you firstly encoding it, then transferring it to latent space of B, and then transferring it back to latent space of A. So F, G are applied sequentially, and encoder of A gives you this CA1. And then this difference is just the difference between CA1 and which was the original latent space vector, and the one you got after transferring it back and forth. And this loss is like similar to this one, which was just predicting A based on this it's CA tilde, which was a transferred one, and then you have a weighted sum of these losses. So the training procedure, we first pre-trained a DAE model for each style separately on the non-parallel data to get the latent space of styles. Then we alternately apply the cross-projection strategy and cycle projection enhancement on parallel data and non-parallel data with losses LS and LC. So straightforward semi-supervised methods. We also introduce another two semi-supervised methods as a baseline to provide a more comprehensive comparison with the proposed CPLS model. The two semi-supervised methods are built from different perspectives. So data augmentation via retrieval. So these are two other methods basically which they're proposing. So data augmentation via retrieval. One semi-supervised baseline is from perspective of data augmentation. In order to alleviate the overfitting issue caused by small-scale parallel data, we propose a simple but efficient method that augments the parallel data by retrieving pseudo-references for the non-parallel data, denoted as DAR model. Okay, so pseudo-parallel corpus construction. We employ Lucene to build indexes for non-parallel corpus of each style. Then the pseudo references are retrieved based on the TF-IDF score to build a pseudo parallel corpus of style SA and SB. We first sample 80,000 samples in style SA as queries. Specifically, each query searches a pseudo reference from the non-parallel corpus of style SB according to the TF-IDF based cosine similarity. The sampled query is therefore coupled with the pseudo reference to form a training pair. We also conduct the same operation that uses sample query from SB to search from SA. After searching from both sides, we construct a pseudo-parallel corpus in the size of 150,000 pairs. With a pseudo-parallel corpus, the model is exposed to more information and thus the problem of overfitting can be mitigated to some extent, though the relevance of the content between the input and the pseudo-reference is not guaranteed. The encoder could better learn to extract the language features, and the decoder could also benefit from the weak contextual correlation information. All right. So basically, what they're talking about is this. They wanted, since small amount of data set often leads to overfitting. So what they basically did was, uh, you in the non-parallel data set. So basically, in the data set of style A, they randomly sampled 80,000 sentences as queries, and then picked up sentences from style B corpus, which were close in the cosine similarity of TF-IDF based features. And they did this the other way around as well. And in net, they got 150,000 pairs. So the training procedure, in the training stage, we first trained a sequence-to-sequence model on the pseudo parallel dataset and save a checkpoint every 2000 steps. We then calculate the blue score of checkpoints. We then on the validation set and select the one with the highest blue score as the final pre-trained model. Then based on the pre-trained model, we fine-tune the parameters using the true parallel data. Alright, so now we have a look at the shared latent space model. The second semi-supervised baseline is similar to CPLS that first trains a DAE model on the corpus of each style. Instead of building a bridge between the latent space of two styles through projection functions, in this method, we simply share the latent representations by cross-linking the encoder and decoder denoted as SLS model. So given a pair of sentences, the encoder encodes it to a context and the decoder directly takes CA to project B tilde. So instead of building a bridge, and we simply share the latent space representations by cross-linking the encoder and decoder. Okay, so they are not like transferring now, they are sharing the latent space representations which they've generated. So maybe this would explain a bit better. So we first pre-trained two DAE models, then we trained the DAE models and the cross-linked S2S models from two transfer directions. Considering the size imbalance, we to avoid S2S falling into overfitting too fast, we alternate the training in the form of training 20-step DAE models and then training one-step S2S model. All right, so I'm not totally clear on this part, so let me try to give it another shot. Similar to CPLS. So CPLS, if anyone's wondering, uh, they gave the full form somewhere. CPLS. Yeah, cross projection latent space. So basically, the novel idea. So the first trainer denoising autoencoder model on the corpus of each style makes sense. Instead of building a bridge, uh, in this method, we simply share the latent representations by cross-linking the encoder and decoder denoted as SLS model. So they directly share it instead of using transferring functions. They are sort of telling each other that this is our latent space representation. So you directly get a context CA from it. You don't have to get individual latent space representations, but I'm not really sure how they're getting the context. Is I guess it would be a concatenation, but I'm not exactly sure. So the experiments. We conduct experiments on two bilateral style transfer tasks and two large-scale non-parallel corpora. DAR model and SLS model are treated as two baselines. In addition, we also train a S2S model with attention mechanism on the parallel data as a vanilla baseline. Alright. So dataset, we construct a Chinese little style dataset with ancient poetry style and modern Chinese style and a English formality style dataset with formal and informal. The text of ancient Chinese poems, modern Chinese, formal English, and formal English. Uh, Ancient. Okay, so these are the abbreviations. The overall statistics are as follows. So Chinese literal style dataset. We consider texts of ancient Chinese poem style and modern Chinese style, which differ greatly in expression, as ancient poems from different dynasties vary in style and form. In this paper, we focus on the poem from Tang Dynasty. To build a parallel dataset, we crawl from the website named Gushiwen that provides ancient Chinese poem, and some are coupled with modern Chinese interpretation in paragraph. We split the collected paragraphs into independent sentences and using punctuation based rules, and manually align the poem sentences with the interpretation sentences to form parallel pair. For the non-parallel corpus of ancient Chinese poems, we collect all the poems from Kuan Tangshi and split them into sentences. So Kuan Tangshi is the largest collection of Tang poem commissioned by the Qing dynasty Kangxi Emperor. Okay, to build the reason we chose the Chinese ballad is that the content domain of the two styles should be close, considering that most of the poems are about natural scenery and sentiments. The most suitable literary form is the lyrics of ballad. All right. So I'm not really fluent with Chinese, so let me just have a shot by using the sentence. So ask the guest why the guest said he wanted to buy an axe and wanted to cut a tree at the mountain. Ask the guest what he's going for. The guest need to get something out of full wooden forest. Uh, Let me try with the English ones. Give them a chance to discover you. You should give them a chance to discover you. I think it is wrong that they cannot go out with her. I think it is wrong they can't go out with her. Okay, so these are like examples, I guess. So formality dataset. The formality dataset used in the paper is built by so this gram one which has formal versus informal. With the release data, we randomly sample 5,000 pairs. We then use a Yahoo Answers L6 corpus as the source, which is in the same content domain as the parallel data, to construct the large-scale non-parallel data. To divide non-parallel data into two styles, we train a CNN-based classifier on the parallel data with the annotation of style and use it to classify the non-parallel data. Experimental setting, we perform different data preprocessing. The Chinese literary datasets are segmented by characters instead of word to alleviate the issue of unknown words. Our statistics allows shows that the average length of an ancient poem is 9 while 17 for modern Chinese sentence. Therefore, we set the minimum length of the ancient poem as 3 and the maximum length of the modern Chinese sentence is 30. For the formality datasets, we use NLTK to tokenize the text and then set the minimum length is 5 and maximum length is 30. We adopt love to pre-train embeddings and the dimensions of the embeddings are set to 300 for all the datasets. The hidden states are set to 500 for both decoder and encoder. We adopt SGD optimizer with the learning rate as 1 for DAE model and zero point 0.1 for S2S models. The dropout rate is 0.4. In the inference stage, the beam size is set to 5. Alright, so baseline. We train a S2S model with attention mechanism on the parallel data as a supervised learning baseline. Since the existing works on textile transfer seldom explore the semi-supervised methods, we propose DAR and SLS model as two semi-supervised baselines. Automatic evaluation metric. Following the work, we employ blue score and style accuracy as the automatic metrics. Blue calculates n-gram overlap, and they use glue, which is generalized blue, to evaluate extent to which sentences are transferred. Uh, they also use a CNN-based style classifier to measure whether the transferred sentence is indeed in a different style. So you can see they are performing pretty well. Their models and on these are all their models, I guess. SLS, DAR, CPLS. So human evaluation, we adopt human evaluation to judge the quality, and so they have this annotation scheme. There are 400 tests in all. We invited four well-educated volunteers to score them. So evaluation shows that it can be seen that blue score and low score of semi-supervised model on almost all the datasets are better than the baseline S2S model. This indicates that model benefit from non-parallel data in terms of content preservation. One interesting thing is that the overall blue score on the ancient poem and modern Chinese dataset are lower than other datasets. This result may be explained by the fact that the edit distance between formal and informal is smaller than ancient and modern. This is pretty convincing. Therefore, it is more challenging for model to preserve the content meaning when transferring between ancient and modern. Among three semi-supervised models, CPLS model achieves the greatest improvement, verifying the effectiveness of the prediction function. However, the gain of CPLS model in the aspect of style accuracy is not that significant. A possible explanation may be the bias of a style classifier. Take the transfer from ancient to modern Chinese. We observe that the classifier tends to classify short sentence into ancient poem as length is an obvious feature. We analyze the sequence, the sentence model generated by H2S and by the CPLS model, and the statistics show that the average length by the text generated by H2S model is shorter, which may lead to the bias of style classifier. Therefore, we adopt human evaluation also. Table 4 shows the comparison of H2S and CPLS model in all datasets. As shown in Table 4, the CPLS model outperforms the H2S model in the aspects of content preservation, style strength, and is in par in terms of fluency. So, a case study, we select the generated results of S2S baseline and three semi-supervised models from the two style transfer tasks due to limited space as shown. Compared with the Chinese literacy style datasets, the formality dataset are less challenging as discussed before. Thus, it can be seen from the table that the generated sentences on the formality datasets are more fluent. For a task that are transferring from Chinese text to ancient poem, the S2S generates shorter sentences while CPLS model generates the sentence that preserve the most content information. So I guess all of this part was like pretty self-explanatory since this was not mathematically heavy. This was just like observations, and the results and why they feel that they got some results. Overall, I think the models did pretty well. You can see almost all the bold ones are in the last row. They are in some tasks they justify why their accuracy fell. So like here they say that S2S models are the average generates shorter sentences, which caters to the bias of the classifier. So the conclusion in this paper, we designed a differentiable semi-supervised model that introduces a projection function between latent spaces of different styles. The model is flexible in alternating the training mode between supervised and unsupervised. We also introduced another two semi-supervised methods that are simple but effective to use a non-parallel and parallel data. We evaluate our methods on two datasets and have small-scale parallel data and large-scale non-parallel data, and verify the effectiveness of the model on both automatic metrics and human evaluation. And their sponsors, so the National Key Research and Development Program of China, National Science Foundation of China, and you have Ruyan, who was sponsored by the Tencent Collaborative Research Fund. So overall, I say that this paper was a great read. I learned a ton of new stuff and hoping to read more papers in the future. If you want to suggest anything, do comment them down below. So thank you guys for joining in, and hope to see you guys the next time.